Late 1942, Allied infantry pushed through the dense coastal jungle of Papua New Guinea and secured the Japanese defensive perimeter at Buna Airfield. Scattered among the earthen revetments bordering the ruined airstrip is a collection of static aircraft wrecks. The physical wreckage presents an immediate contradiction to existing intelligence profiles. Prior to the ground capture, combat reports from airborne Allied pilots had logged encounters with a presumed new enemy fighter operating in the theater. They observed a distinct squared-off wing configuration, fundamentally different from the rounded wingtips of the standard Mitsubishi A6M Zero. This altered visual silhouette caused field intelligence to misclassify the aircraft as an entirely new threat. Some field reports even speculated that the silhouette resembled a German Bf-109, sparking unproven talk of an Axis technology transfer. The operational stakes require a definitive engineering answer. Command needs to know if the enemy supply chain is delivering a completely new airframe or an iterative update to existing platforms. The visual identification barrier stems directly from an aerodynamic trade-off. By adopting clipped, non-folding wingtips, enemy engineers reduced the overall wingspan to about 36 feet. The change was intended to stiffen the outer wing and trim span, and it could sharpen roll response in some regimes, but it also carried handling trade-offs as speeds climbed. However, this modification radically alters the optical profile of the fighter from above and below, breaking the established recognition guides used by Allied pilots and creating a persistent intelligence gap. To manage the incoming reports of this unidentified aircraft, Allied intelligence initiates a sequential naming convention of reporting names. The design initially receives the code name HAP, but the label is soon adjusted to HAMP after objections to the nickname. Only later, once the engineering lineage is firmly established, is it finally tracked as the Zeke-32. The confusion only ends when Buna falls, giving investigators physical access to the wrecks. The wrecks resting in the revetments are definitively identified not as European copies, but as the Mitsubishi A6M3 Type 0 Model 32. This discovery shifts the operation from a standard infantry site clearing task into a high-priority technical investigation. To resolve the intelligence contradiction permanently, a field party from the Allied Technical Air Intelligence Unit, ATAIU, moves on to the Buna perimeter. Formed for exactly these scenarios in 1942, this specialized engineering team operates under a strict operational mandate. Their primary objective is to evaluate, preserve, and recover captured enemy aviation technology before the opportunity degrades. Standard wreckage can provide raw material samples, but determining actual aerodynamic performance and tactical vulnerability requires coherent structural evidence. That evidence starts with intact flight surfaces, engine mounts, and control linkages, salvaged before the site degrades. By late 1942 and into early 1943, Buna is secured and the airstrip sealed with a defensive perimeter. ATAIU engineers enter the revetments and begin a systematic evaluation of what can still be saved. The engineering teams face a rigorous evaluation process. They must assess the dimensional accuracy of the remaining airframes to understand the specific capabilities of the Model 32. The wingspan is measured and verified against the previous flight reports. The measurements match the pilot's reports and lock the variant down in engineering terms. The unit then shifts to recovering usable hardware. Now the problem is procedural. Map the condition of a site littered with advanced fighters stranded in the coastal jungle. And one question hangs over the revetments. How did so many of these airframes end up trapped on the ground in the first place? The Buna runway becomes the aircraft's lifeline. Allied bombing repeatedly craters the earthen surface, flooding sections and breaking the continuous takeoff run into trenches. Once the remaining unbroken length drops below minimum takeoff distance, even intact fighters are trapped as static ground targets. With no heavy earth-moving equipment to repair the damage under continuous aerial attack, Japanese ground command abandons around 15 A6M Zeros inside their protective earthen revetments. The abandonment sequence completely alters the forensic profile of the wreckage. The engineering teams arriving at the airstrip do not find the high-velocity kinetic impact fragmentation typical of an aviation crash site. As instead, the airframes present a specific pattern of distributed localized damage. This damage is entirely static in nature, inflicted while the aircraft were parked. Retreating Japanese ground crews deliberately disable the aircraft before yielding the perimeter. The intent is simple: deny immediate use to the advancing Allied forces. Following the initial sabotage, low-level Allied strafing runs sweep over the static revetments. Ballistic impacts punch directly through the unarmored aluminum skin, severing control cables and compromising internal wing spars. The combination of targeted destruction and random strafing creates a highly complex recovery problem. The Technical Air Intelligence Unit surveys the site and determines that no single captured aircraft remains completely intact. The recovery operation must address 15 separate airframes, each presenting an entirely different pattern of structural failure. Beyond the mechanical damage, the recovery teams face a strict environmental constraint. The moment the Japanese forces abandon the perimeter, the coastal jungle environment begins to attack the compromised aviation materials. The airstrip sits in a tropical heat zone characterized by tidal swamps, persistent rain, and rapid vegetation overgrowth. High-temperature tropical environments rapidly induce galvanic corrosion on exposed aluminum alloys. The constant humidity and standing water act as an electrolyte, accelerating the chemical breakdown between dissimilar metals at rivet lines and primary structural joints. This environmental decay constraint creates a rapidly closing time window for viable structural salvage. If the wreckage remains in the flooded revetments, corrosion can quickly compromise the recoverability of load-bearing spars and critical joints. The recovery operation transitions into a time-critical forensic extraction, constrained heavily by the predictable physics of metal decay. The engineering teams must meticulously inventory the 15 scattered wrecks. They evaluate every ballistic strike and sabotage point to identify which components retain enough baseline material strength for safe extraction. The structural mapping requires precise documentation of the specific damage to each individual airframe. The engineers log the corrosion penetration levels on the exposed aluminum alloys, then noting where the protective coatings have failed. To buy time, the teams post guards at the revetments and keep the area under control while inspections continue. Yet inside the cockpits and forward bulkheads, the engineers find damage driven by human hands, not bombs or weather. Unregulated access to the secured airfield presents the greatest immediate risk to the technical intelligence mission. The primary threat to the forensic integrity of the Japanese fighters comes directly from curious troops moving through the revetments, scavenging the airframes for battlefield trophies. This unregulated activity strips critical instruments and manufacturer components from compromised structures, destroying the technical provenance required by command. Serial plates are one of the key methods for tracking production blocks, material origins, and supply chains. These small metal tags carry metallurgical baselines and factory lineage. Unauthorized removal breaks the paper trail, leaving the recovery operation with anonymous aluminum and far less strategic intelligence about enemy manufacturing capacity. The Technical Air Intelligence Unit faces a severe manpower limit in mitigating this threat. A small team of specialized engineers must lock down multiple dispersed revetments against a constant flow of souvenir hunters. The engineers physically intervene, pulling scavengers out of the cockpits and establishing a hard barrier between the infantry and the aviation hardware. That friction dictates the sequence. Lock the revetments down first, then document. With the perimeter controlled, the engineers begin a standardized forensic record to preserve context before extraction. The intelligence teams employ pro forma checklists designed specifically for field evaluation. These checklists force the engineers to systematically log armor thickness, flight control layouts, and precise tail markings prior to any disassembly. Logging this data while the airframes remain in their original earthen revetments preserves the vital relationship between the damaged components. A rigid inspection path keeps the survey consistent from airframe to airframe. They measure only what answers intelligence questions, canopy glazing, control cable runs, bulkhead interfaces, and instrument layouts, looking for metric standards or signs of captured Allied components. Every detail is tied back to a specific tail code and construction number on the airframe. The documentation process targets distinct identifiers painted on the empennage and stamped into the primary load-bearing structures. The engineers isolate and log specific construction numbers crucial for future tracking. In the best-preserved revetments, the engineers find enough intact identifiers to build a clean chain of evidence. Field logs note construction number 3030 with tail code Q102. In a separate cratered revetment, the same paperwork trail records construction number 3028 as tail code V187. A third heavily damaged airframe is listed as construction number 3032, bearing tail code V190. By linking each construction number to its painted tail code, the unit preserves a usable audit trail for later structural testing and comparison. The consequences of the initial scavenging remain a permanent limitation for the wider site. For several of the 15 abandoned aircraft, the primary manufacturer plates are already gone by the time the technical team secures the perimeter. The engineers mark the production lineage of these specific airframes strictly as unknown. They cannot invent the missing data. This loss of provenance demotes those particular airframes from primary intelligence assets to secondary salvage sources. The team now prioritizes the airframes whose plates and tail codes still support a clean paper trail. With those identifiers recorded, the next problem is physical, moving thousands of pounds of stressed aluminum out of the jungle. The coastal jungle canopy completely denies the use of heavy lifting machinery or standard recovery vehicles at the dispersed revetment sites. The Technical Air Intelligence Unit must execute the physical extraction of the aircraft, relying entirely on manual labor. This introduces an immediate mechanical constraint regarding the extraction hardware. The Japanese manufactured the aircraft strictly to metric standards. To properly dismantle the complex flight structures without inflicting catastrophic damage, the engineering teams are forced to source and utilize specific metric hand tools in an austere combat environment. Using standard imperial tools would strip the specialized fasteners and permanently lock the subassemblies together. Breaking down a stressed skin fighter in an overgrown revetment dictates a rigid technical protocol. The aluminum skin of the aircraft actively carries the aerodynamic load during flight, meaning the engineers cannot simply cut the airframes apart to make them lighter for transport. They must separate the heavy components strictly at the original factory seams. The structural integrity of the wing roots, engine mounts, and rear empennage joints must be perfectly preserved for future flight evaluation. The field disassembly limits dictate that no primary load-bearing metal can be sheared or drilled outside of the established manufacturing junctions. The team painstakingly unbolts the primary structures. They isolate the power plants from the forward bulkheads, detach the main fuselages from the wing center sections, and remove the tail units. The wing sections require extreme care, as the internal structural ribs are highly vulnerable once detached from the central spar. The power plants, heavy radial engines covered in complex manifold plumbing, must be carefully stabilized to prevent crushing their own exhaust stacks when resting on the jungle floor. The engineers meticulously disconnect the internal control cables and fluid lines, manually tagging each connection point to preserve the mechanical routing. This strict adherence to factory seams reduces each aircraft from a cohesive aerodynamic shape into discrete, transportable modules, each weighing hundreds of pounds. Moving these isolated modules out of the jungle presents a severe handling challenge. The extraction teams must manually haul the heavy, uncradled aluminum sections through tidal mud and dense tropical vegetation to reach the Buna beachhead. Without standardized lifting frames or rigid transport cradles, the physical handling must be flawlessly coordinated among the ground crews. Any uneven weight distribution during the manual carry will induce torsion stress on the exposed wing spars. Twisting the bare metal during transport will permanently warp the flight surfaces before they even leave the operational zone. Reaching the beachhead introduces the next critical operational bottleneck for the recovery teams. The extraction route requires loading the components onto shallow draft barges to navigate the local coastal waters. Shifting heavy, UN-cradled aviation components from a soft beachhead onto a floating vessel introduces severe structural risks. The barge deck is unstable, moving continuously with the incoming tide. If the manual rigging is misaligned during the load transfer, or if the barge shifts unpredictably, a sudden drop will crush the fragile aluminum skin against the steel deck plates. The barge load transfer requires precise balance and spatial awareness. The engineers distribute the weight of the separated engines and fuselages evenly across the open deck of the shallow draft vessels, lashing the components securely to prevent any shifting during transit. These smaller vessels then transport the secured wreckage out of the immediate combat area, eventually transferring the load to heavier shipping for the long ocean transit south. The final destination for the hardware is a secure engineering facility located at Eagle Farm Airfield in Brisbane, Australia. The logistics chain routes the recovered Japanese components to Hangar 7, the workshop long associated with the ATAIU effort in the theater. Inside this massive controlled environment, the operational constraints finally shift. The secure facility provides the level ground and the overhead clearance required to properly map the geometry of the salvaged parts. The engineers unload the carefully transported metric components and lay them out across the concrete floor. The disassembled puzzle pieces are now safely in Hangar 7, but how do you rebuild an aircraft when no single donor airframe is complete? The engineers make a critical selection. They combine components from at least 3 primary donor airframes, filling gaps with whatever usable fittings survive from the other wrecks. They evaluate the scattered metric components laid out across the concrete floor to select the most structurally sound sections. This decision selection initiates the creation of the hybrid testbed designated XJ001. The field teardown preserved the factory mating flanges, making reconstruction possible. The engineers must now reverse that exact process to build a single flyable aircraft. However, mating distinct sections without access to original manufacturer blueprints or heavy factory assembly jigs introduces a severe engineering boundary. The hybrid reconstruction protocol forces the engineers to establish a completely new structural baseline. Combining sub-assemblies from different construction numbers requires realigning the aircraft center of gravity from scratch. Without the heavy steel jigs used in the factory to hold the fuselage perfectly straight during riveting, the team must rely on manual plumb lines and spirit levels to establish the aerodynamic center line. The structural loads and internal control cable paths must align perfectly across the bolted bulkheads. If the mating angles deviate by even a fraction of an inch, the internal flight controls will bind under pressure, or the airframe will violently pull out of trim during high-speed flight. The engineers must manually shim the mounting points and constantly remeasure the load paths to achieve basic ground stability. The resulting aircraft represents a deliberate hybrid, built around the major sections of construction numbers 3030, 3028, and 3032, with additional minor components drawn from the rest of the captured stock. The Technical Air Intelligence Unit conducts exhaustive static ground checks inside the hangar, verifying control surface deflections, hydraulic pressure limits, and fuel flow across the mated sections. They balance the flight controls and confirm that the center of gravity falls securely within the calculated aerodynamic limits. The landing gear successfully holds the combined weight of the 3 spliced sections. The hybrid airframe was aerodynamically stable on the ground, but would it survive the structural loads of combat flight testing? A strict altitude boundary defines the ultimate tactical trade-off between the captured airframe and Allied interceptors. The hybrid reconstruction protocol successfully produced a structurally cohesive testbed, allowing the Technical Air Intelligence Unit to shift operations from the hangar floor to the active runway. The newly designated test asset, XJ001, must now validate its engineering in the air. The fundamental objective is not simply to fly the aircraft, but to break down its aerodynamic capabilities through comparative flight testing. This rigid evaluation method pushes the captured platform through a defined flight envelope against a strictly known Allied baseline. Doing so strips away unverified combat pilot anecdotes, isolating the hard performance corners of the enemy machine to generate actionable data. To map these specific aerodynamic boundaries, Command assigns a Supermarine Spitfire Mark V to fly as the control aircraft. Both machines launch from the Australian test facility and climb into the designated evaluation zones. The test pilots execute a highly choreographed sequence of synchronized stalls, maximum rate turns, and terminal velocity dives. They measure acceleration parameters side by side, forcing both airframes to their respective structural and power plant limits. The pilots fly line abreast, initiating climbing spirals to determine exact stall speeds under heavy gravitational loads. They record manifold pressures, control stick forces, and engine temperatures at every 1,000-foot increment. The side-by-side telemetry sets up the next question: how the A6M3's advantage changes as altitude climbs. The flight evaluation highlights a performance divide that tends to widen with altitude. Operating below roughly 20,000 feet, The Japanese fighter can show a marked edge in roll and turn response against the Spitfire baseline, especially in low-speed maneuvering. But that advantage is not absolute, and it does not flip at a single magical line. As the trials climb higher, the Nakajima engine's output falls away in thinner air, the supercharger struggles to sustain manifold pressure, and the margin in speed and climb can shrink sharply. Furthermore, the high-altitude testing reveals the severe structural sacrifices required to achieve that low-level agility. The technical evaluation proves conclusively that the captured fighter is an iterative development of the standard Zero, not a completely new armored platform. To maintain its extreme maneuverability and low weight, Japanese engineers intentionally omitted heavy protective features. The testbed carries little to no pilot armor, and its fuel system lacks the robust, self-sealing protections Allied crews expect. That design philosophy creates a brutal vulnerability. When hit, the airframe is far more likely to suffer rapid structural damage or fuel fires than a comparably protected fighter. The intelligence teams compile this specific performance map and distribute it across the Pacific theater. Command immediately translates the raw flight test data into strict operational directives for all forward-deployed fighter squadrons. Allied pilots are officially ordered to strictly avoid any low-speed, horizontal turning engagements against the squared-wing fighter below 20,000 feet. Instead, they are directed to leverage their heavier airframes and superior high-altitude engine performance. They must utilize high-speed, high-energy diving attacks to exploit the strict structural fragility of the unarmored target, slashing through the enemy formation and using their mass to escape. The grueling extraction process and the precise reconstruction sequence ultimately yield a measurable combat doctrine, permanently neutralizing the initial technological surprise.